Okay, so I've got a plug A released from rest, slides down a smooth circular glide, smashes into C, becomes embedded in it, and I want to basically find then after that how much this thing slides before it comes to rest. So what I really need to do is I need to break this up into several pieces, right? So I'll call this kind of state 1 up at the top at point B. Then this guy slides down, okay, has some sort of velocity right before it smashes into C, right? So there's like before it smashes and then after it smashes, okay, I have a new, once they become embedded, and then it slides to a stop at what I'll call state 4. So it's actually like a 3-step process: 1 to 2, 2 to 3, 3 to 4. 1 to 2 is going to be an energy problem, again, because I've got velocities at 2 different positions. 2 to 3 is a collision. Collisions, we use impulse momentum so that we can keep the impulse force internal to the system. I have conservation of momentum there. Once those two are embedded, okay, and I have that velocity, then it's going to be a velocity again as a function of position. So we start with energy, then we go to conservation of momentum, and then another energy equation. Now, in that first one, it's conservation of energy because gravity is the only thing acting here, right? So I have KE1 plus PE1 equals KE2 plus PE2. Okay, and again, I need to find my datum, and I'm going to call my datum down at the bottom here. Okay, that's going to be my zero potential energy due to gravity. So potential energy at the final state will be 0. Okay, my kinetic energy initially is 0. So my initial potential energy is mgh, which will actually be r. So that'll be the mass of the plug A, gr. That's my potential energy. Okay, that's going to equal my final kinetic energy, which is going to be 1/2 ma, and I'll call it V2. Oops, did that wrong. 1/2 ma V2 squared. Okay, so from this I learned that the velocity right before it smashes into that plug is the square root of 2gr. Okay, so now we have the collision, right? With the collision, momentum will be conserved because if I take the system combined, because then the impulse will be internal to the system. Let me kind of write the full equation. So I'll have the sum of the moments, the momentum at state 2, plus the sum of the impulses, those are the external impulses, equals the total momentum at state 3, right? And again, what happens when I take the system as a whole, the only force that's really happening here is that impulsive force of those two colliding. But because I'm taking them together, that's an internal force, meaning the plug hits the, what do they call it, block? Yeah, the plug hits the block and the block hits the plug, right? Newton's third law says every action has an equal opposite reaction. So if I take them together, that's an internal force, and an internal force will just cancel out. So I will have no external impulses, and my momentum then will be conserved. Okay, so initially, the only momentum is the momentum of the plug, which will be ma times its velocity, which is the square root of 2gr. Okay, and that's going to equal the final momentum, which is the masses are now combined, so it'll be ma plus mc times the final velocity given like that. So from this I can find the velocity of those two after they've collided and stuck together, okay, to be ma times the square root of 2gr divided by ma plus mc. Okay, so again, we use conservation of momentum for that collision because that impulsive collision is internal to the system, thus is canceled. So for the entire system of the two combined, the momentum is conserved. Now I know V3. So now these two are going to slide, okay, over some distance, and I'm going to use the, kinetic energy at 3 plus the work that's done from 3 to 4, which is going to equal my final kinetic energy at 4, okay? Which for us will be 0 because I want to know when it comes to rest, right? So my initial kinetic energy, or my kinetic energy at state 3, is going to be 1/2 ma plus mc, right? Because now they're stuck together, times ma times the square root of 2gr divided by ma plus mc, this whole thing squared, right? 1/2 mv squared, right? Where I know v at 3, okay? Now, the only work being done here is friction, right? In the direction of motion, right? I've got gravity, normal force, but then friction's the only thing that happens. Friction's always a negative work because it always opposes motion, and that's going to be mu k times essentially the weight, which will be ma plus mc times g, okay, times that distance s that it travels. That's the friction force times the distance equals 0, right? So the work due to friction is that friction force times the distance, and again, that's going to be negative work going on here. From this, I can solve S to be equal to the following, and I'll let you do the math on your own, okay? I know typically you guys like to see numbers, okay? We don't have numbers here. We just have the values, or the variables, I should say, so we plug those in and we get that. But the bottom line is again, knowing the masses, knowing the radius of that curve, I can figure out how far this thing slides from this whole system. And I break that up into individual pieces to figure out what's going on step by step through the process using energy or momentum, depending on if I'm dealing with impacts or if I'm dealing with position or time, depending on what I'm looking for.